All right, so thanks a lot for connecting to the talk, to the attendees, and thank you very much, Marco and Fabrizio, for inviting me and for organizing, putting together this amazing resource for everyone interested in the philosophy of neuroscience. It's great to have this, and it's great to be here. Thank you very much. I'm going to be discussing representations in basically in neuroscience, but also in general. So there's a kind of a foundational belief or insight, if you want, in cognition that is nicely captured by this quote by in Nick Shea's latest book, saying that thinking is the processing of mental representations. As you know, there's also an important minority of researchers who believe that that's nothing like the case. And, you know, Chimera, for instance, says that natural cognitive systems do not traffic in representations. And he takes it that we should think of cognitive systems as a set of interrelated dynamical systems. This controversy is, I think, connected to two different views of what representations are. On the one hand, typically anti-representationalists think of representations along Fodorian lines, perhaps, so as dependent on the existence of something like a language like discrete code over which we compute. But contemporary representationalists have very different views on this, and they typically take representations to be, you know, something that's dependent on simpler mechanisms selected for perhaps causal or informational connections between the mind and the world. We also have related controversies within representationalist camps. So there's this big debate on whether liberal accounts, such as the ones I was just alluding to by Millikan and others, can explain how representations discharge the theoretical role they're supposed to have in cognition. And here you have on the one hand, on one camp, proponents of theories that accord representational status to, for instance, the states of magnetosomes in magnetotactic bacteria, or some states of the optic tectum of toads, on the one hand. On the other hand, those who advocate reserving representational talk for cases such as human cognition, in which it earns its, quote, explanatory keep, unquote. So I think, you know, I have the hunch that this controversies in no small part depend on a way of framing theories of representations as searches for necessary sufficient conditions for something to count as a representation. And I think that's a red herring. That's not the right way to think about what theories of representation should accomplish. I have the hunch, again, that all sets of conditions that don't let in too much will leave out too much. So either you have a very restricted set of conditions or a very liberal one. And I suggest that we try some other route to a theory of representation. And I advocate for letting the core periphery structure of representational phenomena guide our theories. So it's clear that the representational phenomena has this core periphery structure. By this I mean that we have very clear examples of core cases of representation in language, say, or in conceptual thought. We have very clear fringe cases of representations, you know, things that are in the periphery of the representational edifice, you know, hormonal discharges, for example, or Dretski's magnetosomes. And then we have cases in between, perhaps, you know, perceptual states for some people, animal communication for some more people. And so I think it's more interesting or a more fruitful entry point to the question of representation to answer what I've called the centrality question. What is it that makes something a core as opposed to a peripheral case of representation? One way to go about answering this is by using what Peter Godfrey Smith has called minimal concepts when he discusses other things, you know, the Darwinian populations, for instance. And the idea is you have a concept which is liberal enough to accommodate all cases that we might want to call, in this case, representation, in the case that PGS is interested in a population. But that's too liberal, and that's going to be, you know, not be theoretically fruitful or interesting. So you then need to show how some of the conditions bring in the theoretical fruitfulness for application of the minimal concept. So this concept will be more theoretically fruitful when applied to core cases, say. So, in the limit, there might be entities that fall under this minimal concept that can be described much more usefully using non-representational vocabulary, and, not much hangs on whether we want to credit these things with representational status or not. And I take this to suggest that the suggested question is a more fruitful entry point to discussion. I was saying I have a hunch about this thing, and the hunch would be that for phenomena which have a clear core periphery structure, then necessary and sufficient conditions are too blunt an analytical tool, and we need to move to some other more subtle and more nuanced instruments, perhaps the kind of minimal concept framework I was quickly sketching here. Right, so the main contribution of the talk is to show or to argue that information theory in Shannon's tradition provides both one workable minimal concept and also an explication of what takes for something to be a core as opposed to a free-for-all case, or what takes for something to be a fruitful application of the minimal concept. The minimal concept would be something like representations are signals in an information processing pipeline. And here, signal and information processing pipeline should be understood the way that information theory, which I will notate IT in the remainder of the talk, understands them. So the idea would be that representations sit between an encoder and a decoder, so they result from a piece of encoding and look forward to being subsequently decoded. And the kinds of codes that are relevant to information processing are of two fundamental kinds: so source coding and channel coding, which correspond roughly to compression and error correction. So I'm going to be saying much more about this in section 2 of the talk, but the idea would be that minimally representations are those entities that meet the minimal concept, but theoretically fruitful examples of representation will present substantial source and or channel coding. Okay, so that was the introduction. I'm then now going to give you a whistle-stop tour of information theory and talk about source coding and channel coding. Then I'm going to provide a sketch of why should philosophers educated in, say, teleosemantics believe that information theory is actually a theory of representation and a workable one. And then I'm going to be arguing that actually core representational cases do present the kind of structure that's telltale signs of source coding and channel coding. After that, I will wrap up and conclude. All right, so information theory. So for most of us, philosophers and cognitive scientists and some neuroscientists, information theory is often thought of as a mere repository of measures of influence and association among variables. So this comes from, for philosophers, straight from Dretke's groundbreaking work in the 80s, but it's all over the place. It's also in Millikan, Scarantino, Skirms, and many others. So let me just let you, quickly introduce you to what these things mean. So a random variable would be something like a collection of values. So say S1 through Si to Sn, together with the probabilities of each of these values. The first thing we do when we think of something in information theoretic terms is to quantify the quantity of information or entropy of that variable. So we call that H of S, and that's a measure of the uncertainty of the value of that variable. And if you measure that in bits, it's equivalent to this kind of heuristic. It's the average number of yes/no questions one needs to ask in order to find out the value of S. So if you count how many yes/no questions in average you need to ask, then you know the entropy of that particular variable. Now, when we think of association, information theory starts from the following realization. So the entropy of a certain variable can be sensitive to the value taken by some other variable. So perhaps if we know that the value of t is t, we may, sorry, not many, but we may need to ask fewer or perhaps sometimes more yes/no questions in average in order to know the value of S. So for example, knowing the value of a neural variable might result in fewer yes/no questions in order to find out the value of a certain environmental variable. So, in notation, H of S conditional on T being T is possibly different from H of S. And now the conditional entropy of S given T, so this thing here, H of S given T, is the expected value of these conditional entropies given particular values of T. Okay, so finally, the main association measure in information theories we call mutual information, which is, for instance, between S and T, will be the unconditional entropy of S minus its entropy given T. So suppose that the entropy of S given T is 0. So that would be that knowing T gives you all there is to know about S. Then the mutual information would be just the entropy of S. That would be very high as possible. If on the other hand, S and T are independent, so the entropy of S conditional on T is just the entropy of S, we learn nothing about S, then HS minus HS would be 0, and the mutual information would be 0 as well. So this works nicely in intuitive terms. So many other, or most other information theoretic measures of influence are variations on I, or mutual information, or constructed out of similar materials. So for instance, transfer entropy is just a form of conditional mutual information. All right. So mutual information and these measures they're extremely important, and they are crucial to analysis in neuroscience, but they're in a very important sense just building blocks for the main results of information theory. So what information theory is supposed to do is not just to quantify association between a number of variables, 2 or 3 of them, is actually to specify limits to faithful transmission of information through a channel. So we need these things here, these 4 links here, which I'm hopefully seeing my little hand going back and forth, in order to have an information theoretic and a substantial theoretic analysis of a system. So we start with the source, and then we want to get information coming from the source through a channel, which is typically noisy, onto a decoder, which will then use this information for whatever purposes downstream. And we want to do this when channels are typically bottlenecks. So they have, the rate of transmission is not infinite. We have some finite limits to how much information per message we can encode. So we need to do both things. We need to kind of compress things so it gets through a bottleneck, and also protect things so it gets through typically noisy channels. So let me take these 2 things we need to do in turn. The first thing is we need to code the source, which is called source coding. And the idea is the following. We first consider the following problem. We need to send information incoming from the source through a noiseless channel, so no noise right now. And the question we have is how much rate, so how much bits per message incoming from the source do we need if we want to transmit it? First, let's ask losslessly. So if we want the receiver to be able to recover a perfectly faithful copy of the original message, how much can we compress the message? How much rate minimally we need to have this kind of lossless transmission? So we think of the source as generating messages, one of each of the values of this source random variable, one at a time, so that in n draws, in n uses of the source, it has produced a sequence S super n. Okay, so the encoder then uses a rate of R bits to encode each source message. That means that for the whole S super n sequence, it's going to be using R times n bits. So the first crucial result in information theory is this lossless source coding theorem, which says that this rate, you can have lossless transmission of information through a noiseless channel if you encode at a rate that is larger than or equal to the entropy of the source. So the entropy of the source is a hard limit to compression of the source. That's the first important result. So here's a very quick example. So suppose we have a random variable with four values, S1, S2, S3, S4, which each of them has this probability. So S1 happens half of the time, S2 a quarter of the time, S3 a quarter of the time, and S4 0.125 of the time. That adds up to an entropy of 1.75 bits. Now suppose we encode this naively, then we need 2 bits because we need 4 symbols, 1 per each of the values. So we would have this encoding here, and this encoding has a size of 2 bits, right? So 1 bit for the first symbol and 1 bit for the second symbol. That's as we just learned from the theorem, is not optimal. What we can do actually is do this other thing, which is optimal. So if we use just one symbol for the most probable value, and then 2 symbols for the second, and then 3 symbols for third and fourth, then the average length of this transmission will be 1.75 bits. So on average, the rate will be exactly what the entropy says. Now, this is, of course, I've rigged the numbers so that you get a sense of how the thing works, but doing this in general for arbitrary distributions is, of course, a very significant feat by engineers or by natural selection and so on. But you get the idea of how it works. The second thing that information theory does is to provide limits for compression when we accept a certain amount of distortion. So we are no longer interested in lossless, but now lossy source coding. That's what we get in neuroscience. So what we get in neuroscience is lossy pathways, that we call them in different ways, spotlights and filters and task relevance and so on and so forth. But the idea is that we single out some information for transmission and just discard or not care about the rest of information. So in order to do that, we need some way to quantify distortion, right? We want to quantify what error in transmission amounts to. And this is typically done in the following way. We have a function from pairs of incoming and decoded messages onto the reals. And what this does is to give a score from, say, 0 to 1 to every pair of a message incoming from the source and its decoded version. So 0 would be no distortion, 1 would be total error, maximum distortion, and so on. It's very important not to misrepresent what information theory can do for us, philosophers of cognitive science and cognitive scientists. It's important to note and to see that D could be any arbitrary function, and this random variable S hat could have any arbitrary alphabet. So it's not necessary to think of distortion as some kind of deviation from a faithful replica. So sometimes we think of it like that. Sometimes that's the right way. So when we think of, say, retinotopic maps, perhaps we're thinking of it in this way, but it's just not necessary to think of distortion as deviation from a replica. So, for instance, it's perfectly meaningful in information theoretic terms to have distortion between a sensory variable and a motor variable. So you have incoming sensory information and you have motor plans at the other side of the channel. And if there is a way in which some sensory information makes some behavior kind of maximally fitness conducive, say, then you can have an adequate distortion measure. Or you could, thinking of problems in machine learning, you could have a distortion measure between photographs, so vectors or matrices of pixels, say, and written descriptions thereof. So, when you have, you want to summarize a photograph with a machine learning algorithm, you can have a distortion measure between the summary and the photograph. So, different formats, different vocabularies, all of that is game for information theory. So for IT, transformation is a kind of transmission. So the main result in lossy source coding is that for any given average distortion that you may have as an objective, D, there is a minimum rate, R, that can achieve this distortion. And this R is given by the minimum mutual information between S and S hat that still meets the distortion. We don't need to care about the formula. What's important is that there is such a function and it's easy to calculate. There's a very clever algorithm that can calculate it very easily. So for our previous little model with 4 variables, the 0.5, 0.25, 25, etc., this is the rate distortion curve. So here you have the distortion, which is 0.5 means at random, and 0 distortion means perfect replication. And as we would expect, perfect replication requires that the entropy of the source is given on the rate. And if you have no rate, then all you can achieve is behavior at random 0.5. Okay, so that was source coding. And now we move on to channel coding. And channel coding deals with the complementary problem. So we suppose that we have a perfectly optimally compressed signal, and we now want to get it through a noisy channel. So now, we have perfectly encoded this losslessly or lossily, depending on what our objective, as well as possible. Now we want to get this through a channel. Now the channel itself is specified by probability distributions of the output symbols of the channel given the input symbols of the channel. So you can think of this, suppose that we have, for each output symbol, each input symbol could make two output symbols equally likely, or each output symbol could correspond to two different input symbols. That means there is some blur, some noise happening in the channel. This is the way in which information theory conceptualizes this thing. So the main information theoretic quantity to quantify channels is this channel capacity, and is the maximum possible mutual information between X and Y. So it just means the logarithm of the number of distinguishable signals. So what we need to do when we do channel coding is we prepare channel inputs by padding them, by giving them redundancies in a clever way, so that we squeeze them through the channel, and then at the other side we decode the resulting values into an estimate of the input, correcting for any errors. And the channel coding theorem says that you can do that if the rate is strictly smaller than the capacity of the channel. So just to give you an example of how this works, this is the noisy typewriter channel. The idea would be that you have a typewriter here, which is a bit of a ham-fisted person, and for every time they want to send an A, they're equally likely to send an A or a B. When they send a B, they're equally likely to send a B or a C, and so on and so forth for the whole 28 or 26 letters. And then the best way to do channel coding here is to avoid using the symbol in between. So you avoid using B, so you only use A, and then C, and then E, and so on and so forth. So that if you receive an A or a B, you know that that can only have come from A. So you see, you're separating the inputs so that you make sure that you can decode the input losslessly, or noiselessly. So you're kind of, another way to see it is you're introducing redundancies in the input so that you can recover it losslessly. All right, so that was the whistle-stop tour of information theory. And now, why should philosophers educated in the Dretskian tradition, why should they think that information theory is a relevant theory of representation? So what I will do here is I will take you through a useful kind of list of 3 additional requirements that philosophers have typically thought representations should have, and that are not met by purely informational connections, and show you that they might not be met by the measures of association I was discussing in the beginning of section 2, but they are definitely met by the very idea of transmitting information through a channel. So this comes from Jonathan Birch and Julius Morchkova's commentary to a paper in BBS just appeared a few weeks ago. So the first additional requirement that they suggest is that the correlation between a certain detected feature and a pattern of neural activity be exploited in further processing. So the idea would be that you don't just, something is not a signal if it's not exploited downstream. And that's precisely what we get when we focus on source channel understandings of information theory. So downstream consumption of a signal, qua signal, is a prerequisite for the application of the source channel ideas that I just presented. So a receiver is needed for the main ideas of IT to apply. And that's actually Charles Rothkopf has been urging this for some years now. This further processing, Bertrand Smorkova says, ends up guiding action and explaining success. And for natural systems, which we're dealing with brains now, when we are thinking of lossy source coding, distortion measures must be fixed by natural processes. So if you think of artificial information theoretic pipelines, then no, it's going to be an engineer, but for natural systems, it's going to be some natural processes. So it's very reasonable to take a leaf from teleosemantic approaches to representation and say that distortion measures are fixed by something like natural selection or some other natural reinforcement learning regimes, etc. So in a way, you can think of information theory as a formal version of teleosemantics. And it's only better because it's first formal, which helps you calculate, and also you don't need a function for every representation as teleosemantic does. It's a function for every information processing pipeline, for every channel. That's less functions, and it's easier to think that a reinforcement learning regime could give you that, and then the fine-grained function per representation. And the third requirement that they focus on is that misrepresentation has to be possible, and this helps explain unsuccessful action. And as it just suggested, information theory revolves around the notion of faithfulness in transmission. So the extent to which a decoded message corresponds to or fails to correspond an original message. So quantifying misrepresentation is actually the very aim of information theory. That's what it does. The philosophical dictum coming from Grice and also from Dretske and many others that there is no misinformation, even if it's true, is beside the point. So there might not be misinformation, whatever that means, but there certainly are misdecodings. So there certainly are instances of decoding which get it wrong, given the distortion measure at hand. All right, so in the kind of main part of the talk, I'm going to be discussing how codes can help us understand core organizational status. So remember I said that if you conjoin the informational minimal concept with the idea, so the information minimal concept was that representations are signals in an information processing pipeline. And then I said that means that they have to be encoded on the one hand and decoded on the other hand. And therefore, we've also learned that the two main encoding or information processing duties are source and channel coding. So the kind of conclusion would be that core examples of representational systems should present substantial source and or channel coding. So that would be a prediction of the account. And how do we get a grip on what counts as substantial coding? Well, we do through the source and channel theorems that I just very quickly introduced. So those source and channel theorems give us a notion of what counts as optimal coding, and therefore we get we get an idea of what counts as substantial if it approaches optimality in some way or other. So what I've said, what I've urged, or perhaps suggested, is that this is not a coincidence. So our representation attributing practices gravitate towards this kind of systems which present this kind of substantial amounts of coding. So the prediction would be that representational systems typically present, so that the typical or core instances of representational systems typically present behavior and properties that in fact are just instances of source and channel coding. I'm going to suggest that that's the case for a number of different examples, at least. So first, for source coding. So the first thing to say is that source coding is at the very heart of what Tenenbaum and colleagues, Gershman, Horvitz, and Tenenbaum call the converging paradigm of computational rationality in cognitive science. So which is identifying decisions with the highest expected utility while taking into consideration the costs of computation in complex real-world problems in which most relevant calculations cannot be approximated. So, the main things to notice is this highest expected utility things in which relevant calculations can only be, costs and approximations. So lossy source coding, so optimally trading off size and accuracy, is an essential ingredient of this idea of computational rationality. It's one that is familiar to neuroscientists since the efficient coding hypothesis was first introduced by Manolo in the 60s, the idea that sensory relays recode sensory messages, extracting signals of high relative entropy from the highly redundant sensory input. He also says in the same paper, the current sensory situation is represented in a concise way that's just source coding, which simplifies the tasks of the parts of the nervous system responsible for learning and conditioning. This efficient coding hypothesis is very much alive. Lots of papers deal with this kind of efficient coding ideas in different ways, calling it like this or not calling it like this, but using this kind of tools. But it's sometimes taken to be a purely standard system, a standardized business. So source coding, as I presented, involves both encoding and decoding. That's what we call a code or a codex. So a code means both encoding the thing, getting it through the channel, and then decoding it. And you need both things. So it's kind of a misrepresentation of what information theory is saying, to take the efficient coding hypothesis to be just about the sender side. It's kind of interesting that some people have said recently things like, there is as yet no comprehensive theory connecting ECH and the Bayesian brain hypothesis. And yes, there is. It's information theory. So the right way to read, I suggest, Bayesian brain hypotheses is as theories of decoding optimality. And by the way, and I'm not going to be talking about this here, but this opens a potential explanation of Bayesian anti-patterns, of the ones that Eric Mandelbaum and many others, well, but basically Eric, for us philosophers, has been urging in the recent past. So this anti-patterns would correspond to circumstances in which coding optimality diverges from Bayesian optimality. But I'm happy to talk about this during the Q&A. Moving now to concepts and cognitive psychology. This is, I don't know if you can see, I have like a window here. I hope you can see it. Anyway, so Eleanor Roche, which is the mother of the probabilistic turn in concept research, says this: what one wishes to gain from one's categories is a great deal of information about the environment while conserving finite resources as much as possible. This is, again, so this idea of getting a great deal of information while conserving finite resources is just, I mean, it's just a lay person, formulation of what source coding amounts to. And contemporary models of categorization are actually more explicit about this. So the sustained model of category representation is explicitly presented as a compression scheme. The simplicity-based account of unsupervised categorization is actually said by Pothos and Chatter. Central principle in categorization is the minimization of code length. So these ideas are very much at the heart of the probabilistic turn in concept research. And to give you a final, next to final example, in natural language, you find the descriptions of things as approximating optimal trade-offs between complexity of vocabulary or syntax and expressiveness, informativeness, or accuracy. So, for instance, Simon Kirby and others in immensely influential papers say things like compositional structure in languages arises when language is under pressure to be both learnable and expressive. And what they mean by learnable is languages which permit the formation of compressed mental representations are easier to learn than those which do not. And this is for syntax, but it happens just as well for the lexicon. So there's a flurry of recent research on how some particular semantic families are apparently optimally source coded. So, for instance, for kinship terms in Kemp and Reiger's paper from 2012, or work by Zaslavsky and colleagues for color. And there's a recent review in Gibson in Intrinsic Cognitive Science, I think it is. Good. So just a final point, because machine learning is typically more mathematically articulate than others, you get these ideas much more clearly here than otherwise, than in other places. So Benji and colleagues say, in a very important explanation of representational learning, or review of representational learning in machine learning, they say that good representations are expressive. And what they mean by that is a reasonably sized learned representation, reasonably sized, can capture a huge number of possible input configurations. So a huge number in the input, reasonably sized in the representation side. So again, source coding. And this is sometimes expressed as nonlinear dimensionality reduction by Benji and others, and also by Tenenbaum and colleagues. To give you examples of what this means, this is from the famous ISOMAP paper by Tenenbaum and colleagues from 2000. And here you have a very low dimensional representation of a space of pictures of a sculpture. So the idea here is that you have pictures which are 64 times 64 pixels, so 4,096 pixels. So a 4,096 dimensional vector space. And just by giving 3 axes, so lightning direction, up, down pose, and left, right pose, you can have a perfect low dimensional, or very, almost lossless low dimensional representation of this space of faces. So again, from a 4,096 dimensional vectors to 3-dimensional vectors, so extremely high compression. neuroscientists and cognitive scientists, and perhaps most of you people are more familiar with eigenface research. And here the idea is that it turns out that the space of faces is very much amenable to description via principal component analysis. And just by having, a quarter of variation in principal components, you can have almost perfect reconstruction of faces. And again, here you're looking for dimensionality reduction. Good. So that was trying to show that codes and core representational status go hand in hand when it comes to source coding. And now I'm going to be discussing more briefly that they also do so for channel coding. First, perhaps we should have, we're going to be clear on a, philosophical perhaps of difference between source coding and channel coding. So source coding, as I've been discussing it just now, is an operation on the relation between representational vehicles, signals on the one hand, and the representata source messages on the other hand. So between mind and world, or brain and world, signals and representata, whereby we sacrifice distinguishability among representata in order to gain compressibility. So we are establishing a relation between the representations and what it is that they represent. On the other hand, channel coding is not like that. It's an operation on the set of representational vehicles, qua vehicles. So it's a set on the system by which we represent, not on the relation between this system and the outside world, or or the extra information processing world, so to say. And channel coding is designed or evolved to be resistant to noise in the sense that the decoder can recover the original signal. So there's this difference between source coding and channel coding. So what would be one common behavioral expression of error correction in evolved systems? So one would be the use of systems of signals that are easily distinguishable from one another. So if you have systems of signals which do not overlap in some space of vehicles, then that's exactly the trick we were using when channel coding for the noisy typewriter kind of channel, right? So we were taking out signals and sparsifying the space of signals so that they are easily distinguishable from one another. And this is what happens all over the place in the brain. So sparse coding is like that. In sparse coding, this is from a famous paper by Pérez Oribe, but there are many others, overlaps between individual representations are less likely than if each representation uses a large proportion of the available neurons, limiting interference. So the idea is that you are actually, so sparse coding, among other things perhaps, is just noisy typewriter style channel coding. Synchronized neural activity is another example. So that implements summation. So here I'm referring to the kind of activity you get again all over the place, whereby a population of neurons fire in synchrony for extended periods of time for different purposes in the brain. And synchronized neural activities inhere in fewer neurons upstream, which implement via the tau of the neuron summation rules that robustly tolerate noise. So because there are summation rules, so for instance, suppose that we have to communicate 1 bit downstream, and three of us say it was 1 and 2 of us say 0, then the decoder will decode 1, which is likely to be the case because there was a majority of 1s and a minority of 0s. That kind of idea. So, and this is given by Butsaki and others as explicitly presented as a noise management strategy. And finally, for people working in dynamical systems, you have these ideas by Rabinovich and colleagues that the kinds of things that he would like to call representations are noise-resistant transients in neural trajectories. And they are noise resistant because they are metastable. So you have like small basins of attraction that don't, keep the thing there forever, but they have this kind of metastability thing, which kind of helps these transients stay stably so for the duration of a certain neural trajectory. So all of these are noise-resistant strategies. The same you get in language. So here the theory of vehicles is, at least one of the theories of vehicles is phonology, and the two one of the main explananda in phonology is this apparent cross-language preferences in sound inventory. So the fact that given the possibilities of the phoning system, we should see, or you should hear many more sounds than we actually do, and that's a puzzle. Why do we just, apparently languages just restrict themselves to this sparse set of the possible sound configurations? And there are two main ideas here. One is the idea of dispersion, and the other is the idea of quantal theory or quantal characteristics of phonology. And they work as follows. So dispersion is the idea that the repertoires of sounds found in natural languages can be explained by a model that maximizes the distance between these sounds in acoustic space. So what you do is you have acoustic space and you position just your signals such that they are as far away from each other as possible. And then quantal characteristics is this idea that you have a continuum in the articulatory parameter, but then only you have saltation in the acoustic parameter. So you can produce all of these things, but you only hear this thing and that thing there, right? So you only hear two acoustic parameters. You're going to quantize the acoustic space when you have a continuous articulatory space. And both these quantal characteristics and dispersion theories, which are the two main theories, are to be expected if phonological systems are the result of channel coding. So dispersion would describe one obvious way to shield a signal from noise. So you just use a few points in the space of possible signals and as far away from each other as possible. Again, like sparse coding in the brain, like noisy typewriter kind coding. And quantal characteristics would correspond to the optimal way to decode dispersed signals. So you just use one single output signal for a whole region of input signals, which is what our noisy typewriter decoder did, right? So he would receive, or she would receive, they would receive an A and a B, and they will always decode that as one single input, A or whatever, right? Because you have to have these two things in tandem. So you need dispersion on the one side and the quantization on the other side. Okay, so let me just wrap up and give some concluding remarks. So what I've been suggesting is that when we think of representations, we're implicitly thinking of entities. I said that are signals in an information processing pipeline, and that means that they first communicate a great deal of relevant information about the world in an economical way. That's source coding. So great deal of information, but being economical. And then through systems of noise-resistant vehicles. So vehicles which are clearly distinguishable from one another or constructed with the right amount of redundancy. So it's kind of interesting that information theory reaches the conclusion that you need this somewhat paradoxical or apparently redundant behavior. So you first squeeze out all redundancies from the incoming signal, from the source that the world, so from the value that the world produces. But then once you have compressed that will be source coding, you need to reintroduce redundancy, but now calculated so as to resist processing through a noisy channel. So you first squeeze out redundancy, then add it in again. And, you know, it's kind of interesting, I think, that you see that natural systems of representation have this, you know, two behaviors, right? So they first, you know, do source coding, and they secondly, they reintroduce redundancies. I think that's a nice, nice evidence for the kind of ideas that I'm trying to suggest here. Okay, so that also suggests that representationalist, so information theoretic, because I didn't say at the beginning, I said that non-representationalists a la Chemero, they favor dynamical system theoretic treatment. But of course, my point is that representationalist theorists are actually getting perhaps somewhat unwittingly at information theoretic explanations. So what the foregoing discussion kind of suggests is that representationalists that is information theoretic, and non-representationalist, that is dynamical system theoretic, explanation strategies sit on a continuum. So some systems perhaps can be fruitfully treated as a sole result of information processing. So, computers perhaps are like that. So you can treat a computer as a dynamical system, but because it is so well shielded and, it's both source coding and channel coding are so pervasive and well done, you can actually make do with just information processing formalisms. Others, on the other hand, only surrender to a full, perhaps dynamical system treatment. So there's no way to understand. So perhaps there are systems, cognitive systems, and I'm sure there are, over which you can gain no purchase by applying information theoretic notions. So those things would be representation-less cognitive systems, and they would only surrender to a full dynamical system treatment. But most typically, both formalisms would be useful. So it's ridiculous, I think, I respectfully suggest to kind of shy away from the formalism of information theory, ideologically, to say. So most typically, both formalism will be useful. So if you're interested, this paper I'm citing here by Beer and Williams is a very nice description of the same mechanism, both in information theoretic terms and in dynamical system theoretic terms, and you get purchase from both descriptions. So kind of to go back to what I was saying at the beginning about the two ways of understanding representations and so on. So you have this Fodorian perhaps view of cognition that says that if you want to transform sensory events into behavior, if you want to do any significant, interesting cognitive work, that would force your system to a configuration of, that will force neural circuits to configure themselves into information processing circuits. So they will be forced to implement exquisitely sophisticated channel-coded systems of signals and exquisitely source-coded meanings. So there's no way to kind of get away from this kind of exquisite channel at source coded situation, so to say. And the radical anti-representationalist view of cognition is that information processing descriptions are never theoretically useful. So there's no way to, so it's just never going to be the case that cognition proceeds in the way that information theory suggests by, shielding signals from noise and compressing information so that it gets to the other side and so on. And I have given some reasons to think that this second view is true. It's not the case that information processing descriptions are never theoretically useful, and I think we have good reasons to doubt that things also work in the way the Fodorian view of cognition says. So we have no reason to think and good reasons to doubt that cognition always works in either of these two ways. And that's it. Thank you very much.